Okay, let's start today's seminar. Today's speaker is David McKeen from TRIUMF. He'll talk about accelerating Earthbound dark matter. Please start.
Okay. Yeah, thank you very much for the invitation and the opportunity to talk about some recent work that I did with a student of mine and David Morrissey, Marianne Moore, and in collaboration with Maxime Pospelov and Hari Ramani. And so this is the archive number if you want to go and look that up. Somewhat recent paper. And the title of this talk is the same as the title of that paper. So it's Accelerating Earthbound Dark Matter. So I guess I can just kind of, by the way, if you have any questions, just feel free to jump in and ask and I can answer them along the way or attempt to. Okay, so this talk, of course, has to do with dark matter. And so, you know, when you give these talks, you have to show a slide like this that describes all the reasons that we believe that there is dark matter permeating our universe. So the evidence comes from a number of different sources, and it spans, you know, a large range of physical scales. So kind of from the kiloparsec scale, as illustrated here with this galactic rotation curve, up to basically the size of the visible universe. So looking here at the matter power spectrum on extremely large scales from the large scale structure of the universe. So furthermore, you know, so these pieces of evidence tell us, of these observations tell us that there's, you know, something that we that's exerting gravitational force, but that we don't see. The success of primordial nucleosynthesis is very strong evidence that this stuff is non-baryonic and very different from all the matter that we've observed here on Earth. And so in particular, the deuterium abundance sets a very firm upper bound on the amount of baryonic matter that you're allowed to have in the universe. And then furthermore, of course, you know, looking at the cosmic microwave background and the in detail and looking at the anisotropies in detail gives us an exquisite measurement of the amount of dark matter and normal matter in the universe. And in particular, there's something like 5 times more of this dark matter than there is normal matter. So, you know, this is stuff that we all kind of have known for a long time. And the consensus picture of the universe, and in particular, actually our galaxy in the universe, is summed up in this picture here, which is an artist's rendition of, you know, what the Milky Way looks like. So it's a nice spiral galaxy. We live, you know, somewhere, say, over like here. Actually, maybe I'll draw some picture like this to represent the sun. We live over here, kind of in the outskirts of the Milky Way, and then the Milky Way itself is embedded in this large halo of dark matter. So that's the picture that we get from the growth of structures, gravitationally bound structures like the Milky Way, is that we sit in this very large diffuse dark matter halo. And inside that halo, there's dark matter and the Earth, you know, kind of moving around, orbiting around. In particular, the Earth is orbiting around the center of the Milky Way with velocity of, you know, order 10 to the minus 3 times the speed of light. And then we have, you know, a whole bunch of dark matter here. And if it's kind of something that you can imagine describing in a particle sort of nature, and all of these guys are moving around in random directions, since they don't interact very strongly, with velocities kind of that same order, something like 1/1000th the speed of light. And so, you know, we're particle physicists, and we would like to understand physics at a fundamental level. And so, if this is the picture that we we think we live in, it would be very nice to figure out what this dark matter is and a little bit more about its fundamental nature. Sorry, I don't know if you guys can hear that, but they're cleaning outside my office since it's 6 p.m. here, but hopefully that's not too annoying. Okay, so how do we figure out whether this picture is actually correct and that we're sitting in this halo of dark matter particles, and if we are, what their properties might be? And so the most straightforward thing you can imagine doing is making use of this halo and the dark matter that we're moving through to do experiments that are broadly termed direct detection experiments. And so the basic idea is pretty simple. So here we have I've just drawn kind of a cartoon of the underlying idea, but in that case we have dark matter from this halo that we're moving through, and it's moving relative to us with a velocity something like 10⁻³ times the speed of light. And this dark matter, we're moving through it. There's some amount of it. Maybe if it weighs as much as a proton, there's about one of these dark matter particles in every cubic centimeter that we're moving through. And occasionally, if this dark matter has non-gravitational interactions, which we have good reason to believe is the case, if that is the case, then occasionally this dark matter will hit a nucleus in some detector that we've instrumented and scatter on it through these non-gravitational interactions. And so what happens is it gives a bit of a kick. Some of its kinetic energy is transmitted to this nucleus, which then flies off with some appreciable kinetic energy. And since this is a normal particle that we have sitting inside of a very sensitive detector, then we can hope to identify it and to record this the recoil energy, how much, which is related to how much momentum the dark matter transmits through this scattering. And if you go and run through like the basic kinematics of this sort of experiment, you can compute what this recoil energy is as a function of the velocity of the dark matter that's coming in. And so you take the standard value of something like 10⁻³ times the speed of light, plug it into this formula, and if the dark matter has a mass that's kind of not too dissimilar from the mass of normal matter, say something in the GeV range, maybe 100 MeV or maybe 100 GeV, then you get recoil energies that are kind of in the tens of keV ballpark. And we've designed lots of experiments that have sensitivity to energy depositions of this scale, and gone and done extremely sensitive experiments looking for these things. So far we haven't seen any incontrovertible evidence of this sort of process happening, and so we can sum that up in the following plot, which characterizes the strength of the dark matter interaction with nuclei or nucleons. So that's the vertical axis here. So that's characterized in terms of a cross section, and that can be related to the dark matter mass here on the horizontal axis. And we can draw exclusion plots from a whole host of experiments here. And the these experiments, even over the course of my career in physics, have really improved quite a lot on our understanding of dark matter and its potential interactions with normal matter, and set extremely strong limits in this parameter space. And so so these interactions here, kind of at this say 10⁻40 square centimeters, 10⁻38 square centimeters, something that interacts through the Z boson of the standard model. So weakly might you might expect it naively to have a cross section to interact with standard model that lives up here. Something that interacts through, just exchange of the Higgs boson is kind of down here near close to the current frontier. So those are the, typical kind of candidates for dark matter and that have non-gravitational interactions with the standard model, so-called WIMPs. So interacting through the, weak gauge bosons or the electroweakly charged Higgs. But it's interesting to also think about potentially what happens if you go further up in this parameter space. So if we go up in this direction, is that totally excluded, or is that allowed by the data? And the way that these plots are typically drawn, it's not always obvious what's going on up there. So let's think about that. So let's think about dark matter that interacts quite strongly actually with the standard model. So if that's the case, then there's a qualitatively different regime that you live in. And so the point is basically, so for strongly interacting dark matter, okay, so strongly interacting, and then I have an asterisk here, and that maybe it's hard for you guys to read, but this asterisk means, just stronger than weak. So the upper sort of portion of that dark matter interaction plot, not necessarily the strong force or QCD, but something stronger than weak. If that's the case, then there's a lot, in that part of parameter space, kind of by definition, the dark matter scatters quite effectively on normal matter. And so this halo of matter, of dark matter that we're moving through, the dark matter that impinges on say the atmosphere or the Earth itself, scatters quite efficiently before it reaches these very sensitive detectors that are deep underground to avoid various backgrounds from cosmic rays. And if that's the case, then they scatter efficiently, and then they in general will thermalize with the normal matter that we're made of. And so so what happens is then these dark matter that are moving through the Earth and scattering somewhat efficiently, they thermalize, and then their velocities are brought down. Their velocities relative to us, our detectors here on Earth, they're brought down to a much smaller value typically. If their mass is something like a proton mass, then they tend to have a temperature that's kind of, say, near the surface of the Earth, something like room temperature-ish, something like 10 to the minus 2 electron volts. And if that's the case, then their velocity is like a millionth of the speed of light, not a thousandth. And so the recoil energy that these dark matter particles would impart in a direct detection experiment is down by a factor of 10 to the 6 compared to the standard weakly interacting dark matter particles. So because of this velocity squared. So in other words, then if we have such dark matter, the nuclear recoils are well below any conceivable threshold for these direct detection experiments. So what do the limits look like in that case? And so here on the next plot, I can show you a bunch of limits. And so for the time being, let's just focus here on the top left plot. And so this shows a host of different experimental limits that come from the previously mentioned direct detection experiments deep underground. And then a number of other direct detection experiments that weren't run underground, but on the surface or even up in the atmosphere. So, for instance, you could take your direct detection experiment, run it on the surface, you have larger backgrounds, but you have enhanced sensitivity to this dark matter that slows down as it moves through the Earth. And so that's what's done by a number of experiments like CDMS, CREST, Edelweiss, and so on. You could also take basically a dark matter direct detection experiment and put it on a rocket, put it in the atmosphere, and so it has even more sensitivity to this, or has sensitivity to even more strongly interacting dark matter. And so that's what this XQC experiment did, and rules out some of this part of parameter space. And I should just mention here, these cross sections are quite large compared to the range of cross sections that I was showing you earlier on the canonical direct detection experiment plane. In addition, you can look at the existence, the lifetime of long-lived isomers of things like tantalum. So strange excited nuclear states that live for a long time and would be de-excited by this strongly interacting dark matter. And you can set limits in this parameter space. And so, there's a couple of, little corners here that are maybe open or maybe not open, but the situation gets even more interesting, actually, if you think about maybe not, having very strongly interacting dark matter, but it's not necessarily comprising all of the dark matter. And so that's what these three other plots show here for you. And they show fractions of this strongly interacting dark matter being either 10 to the minus 3 of the entire dark matter, 10 to the minus 6, or 10 to the minus 9. And so you can see, relatively quickly, even, for kind of percent or just sub% level component of the dark matter, very quickly this parameter space opens up quite a lot. And if you dial it down to say 10 to the minus 9, of course, it's basically almost entirely open. Now, why might that be the case, that you could imagine these like subcomponents instead of the entirety of the dark matter? And I think it's actually a somewhat generic feature of strongly interacting dark matter. And the reason for that is, okay, so it's kind of summed up with this cartoon. So these interactions describe the scattering of dark matter on nucleons through some interaction that's model dependent. And I'm showing here in this gray blob to just be agnostic about what that is. And if you imagine dialing this cross section up, the probability of this thing happening up, then necessarily in the early universe, or at times when this dark matter is quite abundant, then what that means is that processes like this, so I just take this same diagram and kind of turn it on its side, tend to mediate dark matter, anti-dark matter annihilation into, say, standard model stuff. And if you have a large cross section for this process, then you necessarily have a large cross section for this annihilation process. What that means is that it's natural to have very little of this strongly interacting dark matter left over today, because it annihilates very efficiently in the early universe. In other words, it's natural, I would say, to expect strongly interacting dark matter to be just a subcomponent of the dark matter. So that's why I would say that it's actually well motivated, if you're thinking about these large cross sections here, to imagine subcomponents, in other words, fractions of the dark matter made up by this species being less than 1. And so if that's the case, how might you imagine, well, what does the experimental situation look like actually in that case? Okay. So here's a picture of the situation. Let's think now about strongly interacting dark matter that scatters. As it passes through the Earth, it scatters efficiently and thermalizes with the normal matter on Earth or in the atmosphere. Okay, so if that's the case, then as I showed you before. For dark matter that's not too light, the resulting velocity after thermalizing with the normal matter is something like 10 to the minus 6 times the speed of light, typically. And in particular, it can be below the escape velocity at the surface of the Earth. So what that means is this dark matter that then thermalizes gets stuck to the Earth gravitationally. It can become bound and remain here gravitationally bound to the Earth through these scatterings. And so, in other words, then you can have an overabundance relative to the background density of dark matter. You can have an overabundance of dark matter, this strongly interacting dark matter here on Earth. And so you can, make a very quick estimate of how much of this dark matter you could imagine accumulating here on Earth. And so that's, simply just kind of, it's a, simple geometric calculation. So we have, here's the Earth, and it's sweeping through the dark matter halo with a velocity something like 10 to the minus 3 times the speed of light. The Earth has lived, between 4 and 5 billion years, and so it sweeps out, some, million light year sort of distance here through the dark matter halo. The radius, 2,000 kilometers. You can compute the volume of this cone that this, or the cylinder that the Earth sweeps out. And if you know what the dark matter density is here, which we do from a whole host of observations of the Milky Way locally, we know that that density of dark matter is the mass density is something like 0.3 GeV per cubic centimeter. Then you can compute the entire, the amount of mass that's contained within, amount of dark matter mass that's contained within this cylinder. And so if you do that calculation for a dark matter fraction of order 1 for this strongly interacting dark matter, then it's something like 10 to the 42 GeV. So, an enormous number, but a very small number actually compared to the mass of the Earth, but still a very big number. And now, this dark matter is strongly interacting, and so it remains gravitationally bound to the Earth. And if you take this mass and then assume, just for simplicity right now, that the dark matter gets uniformly distributed, ends up uniformly distributed throughout the Earth, which is not such a bad assumption for a lot of the parameter space that we'll be talking about. If that's the case, then you can go ahead and, if the dark matter fraction, the strongly interacting dark matter fraction is 1, then this resulting density of dark matter here on Earth bound to it is about 10 to the 15 GeV per cubic centimeter. So, something like 10 to the 15 times larger than the background density. So an enhancement of, 15 orders of magnitude relative to the background density, which is huge. So, that's somewhat interesting. So, the picture then is that we have, this enormous amount of dark matter locally, but it's moving very slowly relative to our detectors. Okay, so this back of the envelope estimate, you can do a better job, which we did in the paper, and there's been some studies previously of this stuff. So Neufeld, Farrar, and McKeen a few years ago we're looking at similar things, and then actually some of our collaborators were thinking about similar things a couple years ago as well. And basically, there's a simple simple set of equations that you can solve to determine what the dark matter, the local abundance of this strongly interacting dark matter is, as a function of its mass and its interaction strength with with normal matter. And so that's related to the rate of capture. So how often, dark matter that we're sweeping through, how often it gets gravitationally bound, or stuck to the Earth gravitationally. One also has to confront the evaporation rate, because this dark matter gets it thermalizes for a large part of this parameter space that we're thinking about. There's a high energy tail, and that high energy tail can is sufficiently energetic for that dark matter to leave the Earth and become unbound. And so one has to confront that as well. there's and in addition, there's basically sort of two qualitatively different components of the resulting bound dark matter. And they have two different names. So the first one is what we call the genes distribution, which is basically the steady state population where the thermal pressure is what holds the dark matter up against falling into the center of the Earth. And so the thermal pressure differential is what is balanced by the force due to gravity here. And so you get an equation that looks like this that helps you that you can then solve to get the actual distribution of the dark matter inside of the Earth. So going beyond the simple uniform distribution throughout the Earth. And so you can go ahead and solve that and figure out what, as a function of the cross section and mass of the dark matter, then you can figure out what its distribution inside the Earth looks like. And then furthermore, there's actually another different population of dark matter, which comes from the fact that as you capture this dark matter, it's scattering quite efficiently, quite a lot with the matter that the Earth is made up of, and so it takes some, it will end up falling down, trying, it wants to end up where it's supposed to end up according to this genes distribution. So it's wanting to fall down towards the center of the Earth, but it's reaching its terminal velocity because of scatterings on the normal matter. And so it ends up moving more slowly than it otherwise would towards the center of the Earth. And so you can build up this transient population that is, basically coming from the fact that the dark matter is slowly moving through the Earth as it falls towards the center and to find its equilibrium steady state distribution. And so you can estimate what this is by doing a pretty simple conservation of flux argument, and it's related to this population, the number density at a particular radius is related to that radius, and the flux, which is proportional to the velocity of the dark matter as it's through that point. So, anyways, you can do this calculation, and then you can ask for a particular point on Earth. This happens to be something like 1.4 kilometers below the surface of the Earth. This plot shows the density. So here, this shows the scale of the enhanced density. Not sure if you guys see that underneath the zoom window, but in any case, the dark blue is something like an enhancement factor of above 10 to the 14. So that 10 to the 15-ish number I was showing on the previous slide. And then in steps of, factors of 100 from each contour to another. And so down here, what's dominating here is this steady state genes distribution. And at larger masses, you get the enhancement is mostly due to this so-called traffic jam population. Okay, so anyways, so this is a this introduction to this paper is basically been summed up by these slides so far. And the point is, you can have an enormous enhancement, say an enhancement factor over the background dark matter density of a factor of 10 to the 14 in a large part of parameter space. But this dark matter is moving very slowly, and it's very hard for us to see it. If it does bump into a nucleus inside of one of our very sensitive detectors underground, the momentum transfer is just too small to give an observable kick to a nucleus. So even though they're extremely sensitive, they're just, they are not that sensitive, and it's hard to imagine making them sensitive enough to see this population of dark matter. So how do we do that? How do we see this stuff that's enhanced by a factor of 10 to the 14 over the background density that we're kind of and it's, we're swimming in it almost. And so that's the basic point of our paper, is just a couple of ways of probing this this dark matter in this part of parameter space. And so this is the basic idea. This sums up the entire paper, the entire talk, which is the idea is you have this huge background of dark matter just sitting there, and it interacts very strongly with normal matter. So the idea is we can manipulate normal matter, so we can speed that up, slam it into the dark matter, and then now we have a population of dark matter that's moving with velocities much more than 10 to the minus 6 times the speed of light, maybe even as fast as the local halo background population. And if that's the case, then if you can do that through some means, taking this normal matter, smashing it into some dark matter, speeding it up, then if you have a normal dark matter direct detection experiment sitting nearby that process, then this dark matter can go along and give a visible kick to a nucleus inside of a conventional direct detection experiment. Okay, so I've labeled this process kind of something like direct detection squared. So it's sort of like the same underlying process happening twice here, as opposed to just one time in a conventional direct detection experiment. Okay, so the first way of manipulating normal matter to smash it into the background, or the local huge enhancement of dark matter that we have that interacts strongly, in some sense, with us, is to use a beam of normal matter. And so you would probably like to find a beam that's deep underground to avoid a whole host of backgrounds that might make your detection, just like in normal direct detection, that would make that more challenging. So finding a beam underground where the beam, necessarily normal matter, is has an appreciable kinetic energy, is a kind of tall order, something that's not super common, but there are a few such places. And so I'm showing here one of them. That's the Luna experiment, which is located at Gran Sasso. Here's kind of a picture of, this is the Luna area at Gran Sasso, deep underground, something like 1.4 kilometers. There are conventional direct detection experiments also in that same laboratory. So, the xenon experiment nearby, not too far away from it. And what Luna is it's an accelerator that can accelerate protons and other nuclei, other ions, up to kinetic energies, of an order a few 100 keV, or as high as maybe an MeV. And then delivers them to targets. So, does fixed target experiments, basically, where they take these protons and smash them into stuff. And on the next slide, I'll just show you some of their results and why they are doing these experiments. But the point is basically that you can go along and compute what the if you know the beam energy here, the energy of the beam. So in the case of Luna, something like 400 keV kinetic energies. So they have protons in their case, among other things. But if you take their beam and you smash it into some dark matter, then that dark matter goes along and flies into your direct detection experiment that you've located somewhere downstream, and then recoils on a nucleus in that direct detection experiment, giving it some recoil energy. You can compute that recoil energy if you know what the beam energy is. And so that recoil energy is given by this formula here. So it's related to the beam energy. And then there's a whole bunch of kinematical factors here. So the reduced mass between the dark matter and the nucleus here in your direct detection experiment, or the beam particle, and so on. And then it also depends on the angle at which the dark matter scatters at both of these points, the resulting scattering angle between dark matter and normal matter. This is there's a typo here, so that should obviously be less than or equal to. And so there's some, maximal recoil energy, and the idea is hopefully your beam energy is high enough that this recoil energy is above the threshold of your direct detection experiment. Okay, so that's the basic idea. So here's the, like I said, this is the Luna experiment. Has a proton it's being accelerated this way and then steered into different target stations. And why do they do that? Well, the reason they do that is actually for reasons related to one of the pieces of evidence that we use to understand that there is dark matter in the universe. And so that has to do with Big Bang nucleosynthesis. They can do other stellar astrophysics with this machine, but here's a recent paper from a couple of years ago where they did essentially use this machine to do a very nice study of an important reaction for Big Bang nucleosynthesis. So the reaction where you have a proton hitting a deuteron and then turning into helium-3 and a photon. And so because they're underground, they could measure this reaction extremely sensitively in the region of energy that's of interest for BBN. And so here's some data that shows their measurement of this cross section and then the resulting impact on the normal matter density, so the baryon density. And in particular, this is a key piece of evidence that we have that tells us that the normal matter density is much less than the total matter density. So we need dark matter. So yeah, like I said, this is important for, you can do important nuclear astrophysics or Big Bang nucleosynthesis measurements of this kind of a machine. There are similar machines, not just in Italy, but in China. So this thing is called Juna, and also in the United States, there's Casper. And so they're all very, very similar, but for definiteness, we focus on Luna at Grounds House. Okay, so now specializing to the Luna machine, we can ask what the resulting recoil energy. So if we know what the beam energy is, then we know what the nuclear recoil energy is. And so what we can do is, as a function of the dark matter mass, imagine taking this beam, giving it either 400 keV or 1000 keV energy. That's either the solid or the dashed lines in these two plots. And then on the left-hand side, imagine a proton beam. And on the right-hand side, this plot shows the result for a carbon ion beam. And as a function of the dark matter mass, you can ask what the maximal recoil energy is in your direct detection experiment downstream. And so that depends on the nuclear species that you have. So you can have either some light nuclei like helium or hydrogen, or more conventional direct detection nuclei like germanium or xenon. So that these are shown in both of these plots. The basic point is for both, for beam energies, even of order 400 keV, which is what Luna has run at already, you can get recoils, nuclear recoils downstream that are of order tens of keV, so kind of in the ballpark of conventional direct detection experiments. So in other words, you can give a kick to the dark matter, kick it up to something like 10 to the minus 3 times the speed of light. And so what that means is you can take this, take this huge population of very kind of thermalized cold dark matter. There's a huge enhancement, and you can leverage that enhancement and turn it into, with this beam, turn it into a population of fast moving dark matter that you could then see in an experiment downstream. Okay, so here's a picture of kind of our idealized detector setup. So here's this is the beam that we're imagining a beam of 400 keV energy traveling through some distance, let's say order 5 meters, which is kind of what the Luna accelerator does. In this region, this is some vacuum pipe. So basically, there's very little normal matter in it, as little as they can possibly get there, and but there's of course some strongly interacting dark matter that's in that regime, in that region. And some of this gets upscattered and then travels downstream. And then we're imagining some, just spherical detector for simplicity, and it has some size. It's something like 10 centimeters across, reasonable, smallish detector here with a energy threshold that's 5 keV, which is kind of a realistic one for a modern day experiment. So in terms of that plot or layout of the Luna accelerator, previously, then our setup looks something like the following here, where we have this is the beam here getting split into the various target stations for different experiments, and then we're imagining putting a smallish dark matter detector here downstream, like that. And then you can ask, okay, what kind of scattering rates do you see in this detector, given the beam current, which is something like 1 milliamp if you have a proton beam. If you have a carbon ion beam, you can get maybe 1/10 of that. And then you can draw contours in the space of dark matter mass and interaction cross section. You can show contours of the event rate, so the number of events per second in this regime, given this setup. And so, again, these contours are separated by factors of 100, and you can get, even in this very strongly interacting regime, you can get, say hundreds per second, something like that. So, event rates that are quite large. So this is somewhat promising. The difference here between the the proton and the carbon beam is basically all due to the kinematics. And you'll notice, this very sharp cutoff here, and that's coming from just the this threshold requirement of 5 keV. And so there's that ends up giving you any dark matter below here is just kinematically not well enough matched to the carbon beam that it just doesn't get kicked up above 5 keV. So depending on what you want to do, if you want to push to somewhat higher dark matter masses where the kinematic matching between the carbon is a bit better, the carbon and the dark matter is a bit better, then it's good to use the carbon beam. But otherwise, down here closer to the proton mass, proton beam is a bit better to use, and certainly below proton mass. Okay, so that's the basic idea for or the first order idea, and then I guess I will move on to just talk about the second idea really quick, and then kind of sum up probably in the next 10 minutes or so. Okay, so now here's the next idea that we had and that we sketched out in the paper. This one's a little bit more far-fetched, and the reason is that it requires somewhat more advanced detector technology with quite low thresholds. But it has the benefit of having a very easy to implement acceleration scheme. So you don't have to look for underground detectors that may or may not want you to, placing a dark matter direct detection experiment close by. Okay, so here's the basic idea. So again, this shows a cartoon of the basic setup from before, this direct detection squared type setup. And the idea is here, so instead of a beam of dark matter particles that, impinge on this large overdensity of dark matter, instead of a beam of standard model stuff, let's imagine now a hot gas of standard model stuff. And so if we have a hot gas, moving around, there's a bunch of particles going in all, different directions, but moving around relatively rapidly. And in particular, just to kind of focus us, let's, think about the hot gas that's very close to the filament of like a conventional light bulb. And so this gas actually gets up to quite high temperatures. It's kind of amazing, but of order thousands of Kelvin. So kinetic energies of order, electron volts, which I guess is, maybe part of the reason that light bulbs shine in the visible. But anyways, so the idea is to make use of this hot gas where the kinetic energies of order an electron volt. You can heat up quite a lot of them just by turning on the light bulb. And then some of these guys will scatter on the local overdense region of dark matter, or the local overdensity of dark matter, which has thermalized kind of with the background matter, which is at temperatures of order, something like 300 Kelvin, so 10 times smaller temperatures. And so these guys can scatter on the dark matter, and basically the idea is the same as in the beam setup, where this dark matter is kicked up to a higher kinetic energy, then travels downstream to some sensitive detector, which can then record the scattering of the dark matter on a nucleon inside of that detector. And so you can go ahead and calculate, actually, if you know the temperature of this gas, you can go and calculate the temperature distribution of the kinetic energy distribution of the dark matter that's upscattered through this process. And it looks something like this. And the basic point is, okay, so here's this kinetic energy, and then it's characterized by the basically, as long as you have the kinematic matching between the gas particle and the dark matter set up, so that they're not too far apart in mass, then you can have efficient momentum transfers. And if that's the case, then the kinetic energy of this dark matter is something like the temperature of the gas, or its kinetic energy. And so, if you have 3000 Kelvin gas, which is very easy to get near a conventional light bulb, for instance, then you can upscatter this dark matter to kinetic energies of order an electron volt. And if that's the case, then if you have sensitive dark matter direct detection experiments, if they're sensitive enough, to energy depositions of order an electron volt, then they might be able to see this. And so people, there's a lot of work actually being done in this direction to look for very small energy depositions, motivated mostly by the light dark matter and conventional direct detection. But if these things get built, then they can also look for heavier dark matter that's more strongly interacting. And so, yeah, there's a huge amount of effort being put forth in that case. And if you have that, then you can perform basically the same experiment that I was talking about before. And so it looks like this. So you have a light bulb here. Okay, so here's the light bulb. Here's this hot filament, and then there's some region around here, around this filament that's filled with gas that's heated up to a temperature that's more or less the same as that of the filament. And so in this small region around here, then you can have gas at something like 3000 Kelvin. So these filaments are often, you can easily like make them tens of centimeters across. This is not hard to do. You can go and buy them in the store, more or less. And then you can go and compute, knowing how the gas interacts with the filament here, how strongly it interacts, and then self-interacts, the gas, that is. Then you can figure out the sort of volume of this gas that's heated up to these high temperatures. And so, typically it's not a huge region around this filament, something like 0.5 centimeter or 0.5 millimeter, gets heated up to the same temperature, and you can go and compute how many atoms that is, how many gas atoms that is, and this can be as large as 10 to the 17, so a quite large number. And so, so this is kind of the benefit of this technique as compared to the accelerator. One benefit of this technique as compared to the underground accelerator technique, which is that you can get an enormous number of standard model particles kind of moving and potentially hitting the dark matter. Then some of these gas particles will scatter on a dark matter particle and then send it off to a detector that has a very low threshold to detect nuclear recoils. And so in particular, we had in mind a modest amount of carbon monoxide, which has access to all kinds of vibrational and rotational excitations, and could be, and Hari Ramani and collaborators actually were studying the usefulness of this target gas as a direct detection experimental target. And it's not inconceivable that you could imagine sensitivity to EV scale energy depositions in such a detector. On the left-hand side, I've shown basically computation. So I showed the analytical formula for what the dark matter energy distribution looks like after scattering on this hot gas. And so here's just a plot of that same distribution for a couple different dark matter masses. So both the analytical estimate as well as a Monte Carlo simulation, you can see that they all line up quite nicely. And then you can go and imagining this 1 gram of carbon monoxide detector. If you say that it has sensitivity to scatters to dark matter that scatters with an energy above something like 0.8 electron volts, then you can get sensitivities that look like this in that same parameter space of interaction cross section and dark matter mass. And so here we've taken our gas to be argon, which is a conventional, common gas that people put inside of light bulbs. And so you can again get, scattering rates in such a detector of order, thousands or millions of events per second if the dark matter abundance is if this strongly interacting dark matter is order 1 fraction of the dark matter, the overall dark matter. Okay, so these are basically the 2 different detection schemes, experimental schemes that I've sketched out. That's basically what we ended up, basically the point of our paper is just these, sketching these things out and then writing down reasonable estimates for what the event rates would be in such a case. But in addition, we also moved beyond just this simple picture of just characterizing the dark matter scattering through some number called the cross section, some spin independent dark matter scattering on a nucleon, to talk about a somewhat more realistic model, and that's summed up here. So it's just a very canonical, well-studied thing these days, which is imagine that the dark matter is coupled to some dark photon, so A prime. So here's the dark matter. It's coupled to some dark photon, some massive force carrier in the dark sector, with a coupling strength E prime. And then this dark photon can mix with the normal photon with a mixing strength epsilon, and then can scatter on protons in particular, with a strength equal to the charge of the proton. This gives you, you can sum this up at very small momentum transfer in terms of a cross section that looks like the following. So it's proportional to this mixing strength, and then proportional to the squares of both of these couplings. So those are inside of these fine structure constants. And then it also depends on the mass of this dark matter particle. And so as you dial the mass up in general at very small momentum transfers, if you dial the mass of the dark matter, of the dark photon up, then this cross-section falls off. And so now what I'm showing is in the context of this model. So here again are 4 panels, okay, and they differ by the fraction of the dark matter that you imagine this strongly interacting dark matter component to make up. And again, now the this parameter space is again the mass of the dark matter, and then this interaction cross section. But there's a bit of theory behind this, in the sense that these lines are basically show you regions, upper bounds on the strength of this cross section that you could get in a sensible model. So you know, you can imagine taking 2 different values of the dark photon mass. So either 15 MeV, that's the solid, those are the solid contours, or the dashed ones for 50 MeV. And then asking how large of a mixing are you allowed to have for that particular mass. And then requiring that the fine structure constant, the dark fine structure constant, is less than 1. So, you know, if you're motivated by some perturbativity arguments, then that means that if you have a 15 MeV dark matter mass, then you can, you know, realize perturbatively cross sections below this solid line pretty easily. And it's the same in all these cases where, you know, the dark matter makes up this line is the same for the, it doesn't care about the fraction of the dark matter that this component makes up. And then you can do the same, ask the same question for 50 MeV, and you get an upper bound that's down by something like 100 in this parameter space. And then furthermore, you can go and ask, you know, in these experimental setups that I described for you, either, you know, a proton beam at Luna, or a carbon beam, or this argon light bulb with a carbon monoxide detector, 1 gram. What region of parameter space do you get at least 10 events per year? And those are the regions that are above either the solid or the dashed lines, depending on your dark photon mass. So anyways, the interesting thing is that even in, you know, in this model that's a self-consistent renormalizable model description of strongly interacting dark matter that can accommodate all of these different fractional abundances, you can carve out, you know, regions of parameter space, large regions of parameter space that are allowed by all other experimental data, so which are, you know, shown as shaded gray regions, and I've shown before. So you know, this is just a nice proof of principle that this you know, this sort of setup can be realized and carve out parts of parameter space in an actual model, not just in some kind of simplified framework. So with that, I think my time is up. So I will put my my conclusions here, and they are basically the following. So I think, you know, the search for dark matter is super important, right? We have lots of evidence that it exists. It's very easy to imagine that it's a fundamental particle with a mass not so different from, say, the proton mass. The WIMP parameter space, the WIMP region of parameter space, is well motivated, but it's under siege. It's hard to imagine, you know, if you want that to be the case, then you have to kind of contort yourself a little bit more. It's possible that dark matter or a subcomponent of it, then maybe we can learn about the larger component this way, interacts quite strongly with normal matter. If that's the case, finding it is qualitatively different. And so I've just shown you a couple of ways that you might imagine doing that. Other people have also thought of different ways of doing this. And so, you know, we have to have an open mind and lots of interaction. So thanks for your attention, and I'm happy to take questions.
Thank you very much for the nice talk. So any questions or comments?
Can I ask questions?
Yeah.
Okay. How about this dark matter boosted by cosmic ray? I mean, is it possible? I mean, people in some they consider this boosting dark matter by cosmic rays.
Yes. Yeah. And in fact, actually, yeah, McKeen, so one of my collaborators, worked on this, yeah, several years ago, and yes, this is another way of accessing this part of parameter space. But let me see if I can. So we didn't. I guess we didn't put it on the plot, but it would be sort of you know, in this region over here, kind of at masses below in a GeV or so, and in the like 10 to the minus 28 square centimeter region. But it also falls off, like, as you know, the sensitivity also falls off as you dial down the fraction of the dark matter that this component makes up. So yeah, that's another very good way, you know, of leveraging existing observations or existing experiments to look for such stuff. However, it's hard to imagine probing something like a 10 GeV component, because cosmic rays are mostly protons, and so they're kinematically not super well matched to heavier stuff. And so you could, you know, in the case of Luna or the light bulbs that I was talking about, you could imagine having heavier, either a beam made of heavier nuclei or a heavier gas inside the light bulb or something. That's so trying to push up to higher dark matter masses in this case.
Okay. Another question is how about the lower mass of dark matter? So it's not.
Sorry. So yeah, if we imagine going, so in this strongly interacting regime, one has to do different things than what I was describing if you want to probe lower masses. So if you go too light, then you don't build up an enhancement in the dark matter density, because it's moving very quickly. It's moving relatively quickly. Its velocity tends to be above the escape velocity on Earth, and so it evaporates.
Why? Because the dark matter interact with this nuclei in the atmosphere.
Yeah, so I mean, indeed. So if we go and look at yeah, so when you go and, you know, compute the evaporation rate, it's the evaporation also depends. It depends on where the surface of the last scattering is, and so which is, you know, defined by the you know, when the interaction length of the dark matter at that surface of last scattering is larger than the like column density of atmosphere and Earth, then it tends to escape. And so indeed, so even if you have quite fast moving dark matter that interacts strongly, you know, you get slowed down and might not evaporate, but you still lose. You tend to lose more as you go lower and lower in mass, and that's what's happening here on this part of parameter space. And that's why it's the enhancement is falling off pretty rapidly here below 200-300 MeV. And it's basically, you can still retain some of the dark matter, at least locally here on Earth and like inside of the Earth, but it's not it becomes exponentially harder to win as you dial the mass down. So eventually, even though it's very strongly interacting, then the other thing is that it's now no longer kinematically well matched to the atoms, the nuclei inside the Earth and the atmosphere. And so it interacts a lot. It bounces, it tends to hit these atoms, but it basically just, recoils off of them, and that with the same velocity. So the momentum transfer becomes quite inefficient. And so it scatters, and then maybe it turns around, but then it scatters again and then goes back out. Or so it you also need to be able to efficiently transfer momentum to keep these things bound, and that you also lose as you go to lighter masses.
Yeah.
If you're scattering on the nuclei.
I see. Can you consider the interaction with the electron or neutrinos? I mean, not the nucleon.
Yeah, that's another question. That's another, yeah. And if that's the case, then that changes, you could imagine maybe going down by a factor of 1,000 in mass, because if you're scattering on the electrons, but, or at least, it becomes a harder problem in my opinion, I guess. But I think it's something worth thinking about. But it's not something we thought about for a number of reasons. But yeah,
maybe there is no free electrons in the atmosphere.
at least not unless you're like quite high, or I don't know. But yeah.
Okay, I have last questions. I mean, you have in your figure you have a cut at the cross section 10 to the minus 26. So I mean, what happens for larger cross sections? Why the constraints continue?
So there it becomes there are constraints that continue there, and they're quite a lot from cosmology. I guess it becomes hard to imagine a perturbative model that can give you a cross section that large, and I guess it's kind of summed up with these plots here, where this is maybe the simplest sort of model you can imagine. And if you want, this fine structure the dark fine structure constant, you don't want it to be too large. I mean, you could imagine, okay, let's make it 4 pi or something, right? Or I don't know, as large as you can imagine perturbatively. That'll push you up a little bit here by a factor of 10 or something. But it becomes pretty hard to push up to higher dark matter masses. And so that was the main reason for not thinking about things too much larger than 10 to the minus 26 square centimeters, I guess that's one of them. But I mean, if you just take it as a number and then say, oh, well, it could be some composite model, blah, 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 then indeed there are some constraints there. Many of them coming from from cosmology. So if you're up in that regime, then you can actually drastically distort the CMB anisotropies, as well as formation of structure. And so people there have been papers that have looked at this as well. But from a particle physics point of view, then it seems challenging to realize models up there, but maybe they exist. Yeah, but thanks. Yeah, that's a good point.
Thank you for nice talk.
Thanks very much.
So maybe I missed, but in this plot, which value you assume for epsilon? Epsilon is the kinetic mixing of photon and dark photon, right?
Yes, that's right. So I forget what the particular values are, but what the logic is pick the dark photon mass, 15 or 50 MeV. Then you go and look at the limits on the kinetic mixing epsilon as a function of the dark matter mass, and then you go to the largest value that you're allowed. And then fix the
observation?
Yes, yeah. So
okay.
Yeah, so there's a number of experiments that constrain 50 MeV 50 MeV guys, dark photons, and in both cases the limit on the kinetic mixing is kind of something like 10 to the minus 2-ish, something like that.
I
And so,
see.
yeah, so you dial that as large as you can. And then now you say, okay, let me fix alpha prime to be 1. Once you do that, then you get, then this cross section, you know, is the solid line on these contours. And so to be above there, then you would need a larger alpha prime. And yeah, so that's the logic behind how these are drawn.
I see. I see. Any other questions? I see no more questions. So let's thank her again. Thank you very much for the nice talk.
Thank you. Yeah, thanks.
So this is the end of today's seminar.